Hi folks, welcome to section 2.2. 2.2 is all about Newton's laws. This is a big important part of this unit. And we start off by defining this thing called net force. So let's get started. To understand all of Newton's laws, you need to understand what he would mean by net force and what we mean in physics by net force. When we say the word net in physics, we really mean total, but it's not as simple as addition. So this idea of net force has two symbols. I use the one on the left all the time. I never do a good job of drawing this Greek letter, but I will try. This is sigma followed by F. So sigma in math means summation. So you are about to add some things when you see this symbol, and we are about to add some forces. And then very commonly in other textbooks or places, you would see F sub net as the net force. All right, so that's the symbol. I'm going to use this one all the time, but you can use either one that you like. Net force is defined as the vector sum of all forces acting on a system. So a vector sum is different than a regular sum because vectors have a direction to them. And so you've seen a little bit of vector math. You know that like 20 meters per second in the positive direction goes this way, and in the negative direction goes that way. And so vector sums deal with the fact that vectors have direction, and so use the direction to assign a positive or negative value to the force, and then we can add them up. We work in two dimensions, so when we say the net force, we really mean the net force in the x direction, the net force in the y direction, and if you take more physics, the net force in the z direction. So in a three-dimensional world, the net force has three directions to it, and you can combine them into one big net force, but for now we're going to focus on the components of that. So in order to calculate net force, you need to draw a free body diagram. After you do that, you'll need to do a few things to make sure that you show how you're doing the math. So the next step for the free body diagram is to set your coordinate system. Now that sounds really complicated. All you are really doing is you are declaring what directions are positive and what directions are negative. So as long as you do that, as long as you're clear about it and consistent, then everything's fine. We have talked about how to work in two dimensions, and we also just talked about how you have, this is separate from this course, but we focus on the x and the y direction. Because we have net forces in two different dimensions, we are going to find them separately. So one thing that's really important is you want to find components of vectors at an angle. So if you see a vector at an angle, you want to immediately do trig for that to break that apart into two components. Then you can add the x and y direction forces separately. And so you do want to do that twice, right? Once in the x direction, once in the y direction. The last one is possibly combine the net force in the x direction and the net force in the y direction to find the overall net force. This doesn't pop up too much in AP Physics 1, but you want to be ready for it. So I'll explain all of those steps in just a minute. Example 1 is very easy. we have a free body diagram with 4 forces, 2 10-Newton forces, a 5, and a 20. And so, set the coordinate system. You can draw a little set of axes and identify the positive directions. If you want to go even further, you can identify the positive x direction and the positive y direction. Now, I chose this weirdly for a specific reason. I wanted to show you that you can honestly pick any coordinate system you want, and it will work out just fine. I'm just choosing one that I don't think you would naturally choose, because left and down are the ones I just spent a whole unit telling you were negative. Okay, there are no vectors at an angle in this one, and so we're now going to add the x and y direction forces separately. So the sum of the forces in the x direction. Now, you are about to add these vectors, but you have to assign a direction to them. So I assigned the 5-Newton force a positive value, and because the 20-Newton force is in the opposite direction, it has a negative value. So I would go 5 newtons plus negative 20 newtons. And so the sum of forces in the x direction is going to be negative 15 newtons. Excellent. And then I do the same thing for the y direction. The sum of forces in the y direction. And this time it really doesn't matter that much. They're both 10 newtons. The positive y direction is down, so 10 newtons plus negative 10 newtons. So if down was positive, up is negative, and so when I add these, I get a net force in the y direction of 0 newtons. Okay, now when it says possibly combine the net force in the x direction with the net force in the y direction for an overall net force, I would expect you to be able to summarize this. And so, to say what is the net force on this system, let's say the net force is equal to, well, if it's 0 in the y direction and negative 15 in the x direction, then the net force is going to be 15 newtons. And the net force is 15 newtons, well, negative in the x direction is going to be to the right. And so 15 newtons to the right is the net force on this system. So you can declare that. Okay, next example. Now we have a vector at an angle, so I will assign a coordinate system, and then we'll do some trig. Now I'm going to assign a coordinate system that is more sense-making to us. Positive x and positive y, the way that you learn them in algebra class, making a graph. Now, I have this 10 Newton vector at a 20-degree angle. And so I want to set up a triangle. So in the first unit of the course, we only really dealt with velocities at an angle. In this unit, we'll see other things at an angle, specifically forces. The hypotenuse is 10, the angle is 20, so this is the force in the x direction, this is the force in the y direction. So I can set up some calculation here to take care of that. Let's do that with a smaller pen. So for fx, fx is going to be 10 newtons times the cosine of 20. Fy is going to be 10 newtons times the sine of 20. So you just want to take care of that trig real quick. So 10 cosine 20, that is 9.4. 10 sine 20, and that is 3.4. These are newtons. Okay, so those are my components. So now I can continue on. I have broken this apart into 2 components, and just to show that, I'm going to try and make this show up. When you break a force into components, you have now a horizontal and a vertical component. So Fx and Fy that are added into the mix, and they essentially take the place of this 10 Newton force. Okay, so add everything in the x direction. So this is still pretty easy. So I have 9.4 newtons in the positive, and then I have 16.6 newtons in the negative. So 9.4 minus 16.6 is negative 7.2 newtons. In the y direction, this is where I want to stop and pause because I have a lot of forces going on. I have the 10 Newton force up, I have Fy up, and I have the 6.6 Newton force down. So I have to be careful. 10 newtons is up. There's another force up, and that is 3.4 newtons. And then there's a force down, and that is 6.6 newtons. Right. And so I can add these up. So 10 plus 3.4 minus 6.6, and that is positive 6.8 newtons. All right. So this one is like much more complicated. There's a net force in the x direction, that's to the left. There's a net force in the y direction, that is up. And using like the trig that I did in the previous unit, I can put all this together. So you did this vector drill assignment, and this net force in the x direction is 7.2 newtons to the left. This 6.8 newtons is the net force in the y direction. And I'm going to just save you some time in this video. You can do the Pythagorean theorem. I guess I won't save you some time because I want to show you. So 6.8 squared plus 7.2 squared. The net force has a magnitude of 9.9 newtons. And the angle is 43 degrees. So this net force is going to be 9.9 newtons at 43 degrees. Now I haven't used any like cardinal directions, so I'm going to just say above the negative x axis, because that's the direction I drew it. So this example got like a little out of hand as far as complexity, but you can see like the ways that vectors play into things and adding and subtracting vectors based on where they're pointing. That's it.